Hi, welcome back to 3.1 exponential growth. In this video, we're just going to look at some patterns, and hopefully as we go through it, we'll be able to learn something about the nature of exponential growth. And after that, we're going to talk about finite differences, and then we're going to also do some more examples. All right, so for this first slide, I'm going to show you a few different patterns. One is in blue, one is in orange, and one is in green. And then after you see the patterns, you can pause the video and then describe how each pattern is growing. So here's the first one. Okay, that's the first pattern in blue. So it went from two squares to 4 to 6. Then in orange, we have that. And then for the green, we have that. Okay, so go ahead, hit pause, and think about how you would describe how each pattern is growing. Okay, welcome back. So for the first one in blue, as you could hear how I described it in the beginning, went from 2 to 4 to 6. So you can tell it's actually just going up by 2. Two squares are added on the top to get each consecutive term. For the orange, okay, we see a square pattern, right? And it looks like the square side length is growing for each term. So the side length increases by 1. So we have a 1 by 1, then we have a 2 by 2 square, and then we have a 3 by 3. After that, if I had to make predictions, I'd say 4 by 4, 5 by 5. You guys get the idea. For the green one, we can see that the length is just doubling, okay? So the total numbers of squares is actually doubling for each consecutive term. All right, so now we'd like to talk about the growth rate for these. So which one do you think is growing the fastest? So the blue pattern, the orange pattern, or the green pattern. So I wrote down beside it just the number of squares. Okay, so at this point, it actually looks like the square pattern is growing the fastest because it goes 1, 4, 9. It kind of beats all the others. However, if these patterns were able to continue, we would actually see a different winner for the growth pattern. So we would actually see that this pattern far exceeds all the others in terms of growth. Okay, so we now just want to predict the next two terms in the pattern. So for the blue, if we were adding 2 each time, that's how the pattern would grow. For the orange, we see that the square's side length is growing by 1 each time. Okay. So it goes from 1, 4, 9, 16 to 25. Okay, the ones in red are the new amount of squares in the pattern. And then for the green, the one that's doubling, we would get that. And then the next one's going to be a little bit too big to fit in. So I just wrote a 2 by 16. Okay, so that array of squares, 2 by 16, gives us a total of 32. So the pattern would go 2, 4, 8, 16, 32. You can see it's just doubling each time. Now let's take a look at the finite differences. So for the first pattern, the one in blue. So we have the first 3 terms, and I could complete this table to get the 4th term and the 5th term. So we'd have 8 and 10 squares in those. Now let's do the finite differences. Remember, we always do the final y minus the initial y. So we'd have 4 minus 2 to get 2, and 6 minus 4 to get 2, 8 minus 6, and 10 minus 8. So we can see that we get a constant difference in the finite differences. And the first difference is we reach a constant value. So what that means is that we have a linear relationship. So whenever the first differences are constant, it means you have a linear relationship. I can see this one, it's going up by 2 each time. So if I had to give this an equation, I would probably say it looks something like this. So the number of squares is represented by t, and the term number is n, so I'd write 2n. That would be a good equation. So for the first term, there's 2 squares. For the second term, 4 squares. Third, there would be 6. Okay, now For the next pattern, the square pattern, to complete the table, in the fourth term, there would be 16 squares, and in the fifth term, there would have to be a 5 by 5, so it'd be 25. Our first differences, here we go. We get 3, 5, 7, and 9. And if we take a second set of finite differences, our second differences would show a constant value of 2. So whenever the second differences are constant, it means we have a quadratic function, which is a nonlinear relationship. If I were to try to come up with the equation for this, I would say the number of squares, t, is equal to the term number squared. So for the first term, it's 1 squared. Second term, 2 squared. Third, 3 squared. You guys get the idea. Last pattern, number 3. This is the one that's doubling. To complete the table, the fourth term would have 16. The fifth term would have 32. 16 doubled is 32. Okay, now for our finite differences. So what do you guys think is going to happen with the finite differences for this? Okay, you haven't seen anything quite like this yet. So let's go ahead. Here's the first finite difference. So 4 minus 2 is 2. 8 minus 4 is 4. We get 8 and then 16. Okay, notice what happens. We actually get the same numbers that are in the table. They just repeated. If I go to do the second differences, we can expect to get the same result, right? 4 minus 2, 2. 8 minus 4, 4. 16 minus 8, 8. Okay, so the finite differences for this kind of relationship will never be constant. Okay, this is true because a constant ratio of 2 exists between successive terms. So all the terms in the finite differences, they all have a common ratio of 2, meaning you multiply by 2 to get the next term. Okay, and it's not just true in the first set of differences, it's also true in the second set. And this ratio would keep continuing. The fact that there's always a ratio of 2 between the values means it's never going to converge to a constant value. So when there is a constant ratio in the finite differences, it means the pattern has exponential growth. So it's one of the characteristics of exponential growth. Okay, here's our graphs of each pattern. So in the blue, we had our nice linear relationship with a slope of 2, y equals 2x, basically. For the orange one, we had a square pattern. It looks like x squared. So it has like a quadratic growth. And then in the green, we had a doubling pattern. Notice this one just far surpasses the others in terms of growth. So once something starts doubling, as you've kind of seen in the other activities that we did in the other video, when something's doubling, it grows really, really quickly. Okay, I left a link to this in Desmos just because I did want to show you something else here. So here's those 3 equations that are graphed. Notice in the beginning, okay, the linear one is red, the quadratic is blue, and the exponential is green. So in the beginning, the exponential is actually the smallest one. Okay, but it's not until 2 that they actually all intersect. Okay, and then they start growing really, really quickly. Okay, the blue one, the green one, the exponential growth ends up passing the quadratic right at this point, 416. And then after that, you can see it totally grows so much quicker than all of the others. Also, something I wanted to point out, on this side of the equation, the green one that shows exponential growth, it never ever touches the x-axis, kind of like the y equals x function. Okay, so we'll talk about that a little bit later too. Okay, so you have that link in the PowerPoint, so you can always reference this if you need to see what those graphs look like. All right, so that's actually it for the first video. We'll start example 1 in the next video. I'll see you there shortly.